Hi everybody, I hope you're enjoying the workshop so far. My name's Rydval and I'll be giving a talk called Beyond Blue, Developing Unbiased Reflected Light Time Series using High Resolution Surface Imaging. And actually I was supposed to be in Germany, take part in the conference and the workshop in person, but unfortunately there was a clash with another conference, so couldn't make it this time. But anyway. So if we look at different triggering parameters, there's, for example, triggering width. That's something all of you are definitely familiar with. Blue intensity, the parameter that you're learning about just now. Among others, there's also density and different wooded anatomical parameters. And there might also be an option to generate data sets of a high resolution version of blue intensity, perhaps, using certain high-resolution imaging systems. But in general, if we think about these different parameters, we can do so in terms of time, effort, cost, simply the resources that are required to generate the data sets from these parameters. And so what we have actually is sort of going from the left to the right, from relative ease of access and parameters that are generated and produced quite easily to ones that require a lot more effort. But together with this, we also see that generally in terms of signal and also the resolution that we capture, there's also improvement, as generally speaking, as we move from left to right here. And if we look at resolution specifically, we can see that where maybe some of the issues might be looking at blue intensity, because if we zoom in, clearly with blue intensity, the resolution is relatively low compared to some of the other triggering parameters that we see here. We can have a look at some biases that can potentially affect blue intensity values. This might include, for example, the color-related issues that affect the surface properties, the reflectance and brightness properties of the sample surface, and these discoloration issues that can introduce a bias in the blue intensity values can be related, for example, to a hardwood and softwood difference in color and brightness properties, which essentially represents a step change in blue intensity. And the issue can also occur, for example, if we look at living compared to relict or subfossil wood, which can have very different brightness properties. And here's an example of that, where we have this essentially data from blue intensity and density, maximum liquid density data, which agree quite well for the most part, except in the recent period there's a divergence where the blue intensity values they diverge from the latewood maximum density values. And that's related to the color bias in the blue intensity data. Another issue then is related to resolution, and with density data sets as well as blue intensity, what we see is that we essentially do not really have adequate sensors to capture the density profile of rings very accurately, particularly when they are very narrow. And what this means is that with very narrow rings, just because of this sort of hardware limitation, we tend to underrepresent the density, in this case maximum latewood density of these very narrow rings, just simply because we are not able to capture that point of highest density. In another study, Jesper Björklund and others were interested in finding out what exactly is important for determining density and density-related relationships with climate. And essentially they found that the actual composition of the cell wall itself and components, for example, such as lignin, do not actually play or seem to play a very important role in determining density of the wood. And instead, actually, the dimensions, the relative proportions of the lumen and the cell wall actually play a much more important role. So this is quite interesting because essentially it means that we can represent density simply by looking at the 2D anatomical structure and the relative the tracheid dimensions and the relative proportion of the cell wall to lumen areas. So this led us to consider whether or not whether it might be possible to produce a binary representation, a black-white representation of the surface of a sample simply using high-resolution reflected light imaging of the sample surface. And if this representation could then be used to essentially create a new version of a density data set, which would not have the same resolution and color related biases as we see in blue intensity. A bit more than 2 years ago, we started experimenting with different ways of preparing the surface of shearing cores, and essentially to get the smoothest possible and the flattest possible surface. So this involved using microtome blades, also some staining in order to try to increase the contrast, which is important. I'll talk about that in a little bit. So I won't go into the details, but essentially this allowed us to prepare a very flat surface by then filling in the lumina using chalk powder. We're essentially able to get sort of very homogeneous surface when it comes to the lumina. And what we then have, here's just one example of a sample which is processed in this way and also stained. So then we actually image the samples using a high-resolution microscope system. This is actually coupled with a automated sort of mechanized stage, which allows us to capture consecutive image and create a mosaic of the sample, the surface of the sample. So here are just some example shots, and essentially what we do is we compile a mosaic of hundreds of images, individual images, and in fact that's just on the 2D plane, but to account for little bumps and to make sure that everything is in focus, there's also many more images that are taken on the z-axis as well. So at the end of the day, even just with a relatively small sample, or let's say 6 centimeter section of a sample, we're processing thousands of images. Then we basically end up with an image like this, with the unstained and stained section. And then we go through a series of steps to process these images. But actually, one important thing is with regular unpolarized light, what we see is that the light reflects in a range of different ways, which makes it very difficult to achieve high contrast between the cell wall and the lumina in this case. But this is actually quite easily solved using polarized light. So with polarized light, what we get is a much higher contrast, much better visual representation of the structure of the sample. And then taking those images, what we do is actually go through a series of steps with some contrast adjustment, thresholding, and then a binary conversion to end up with these binary black-white images, which should theoretically represent the structure of the sample. Looking at one individual ring, this is sort of what that conversion looks like. So afterwards, here's the result. And a bit of a close-up here. So you can see this is the final image that we then work with and measure. So an interesting side note here is that for this process, or to measure these images, essentially there's no light or color calibration required at all, because essentially we've removed any sort of brightness or color from the equation altogether, just by having this binary black-white, black pixel, white pixel structure of the sample surface. So this is an example of resulting image that we get from this binary conversion. So it's in this black-white format. Then we might actually take a negative of that, which kind of looks like a X-ray density representation of a sample. And the nice thing about this is that essentially we don't have to bother with inverting the data, which we currently have to do with some of the blue intensity data sets, because in this case essentially the inversion is performed by converting the image to the negative. Here we can see an image with blue intensity measurements that you will all be quite familiar with now with the lower resolution scanner-based systems, somewhere around 2400 dpi. And if we look at the binary images, we can actually measure these in a similar way, even using QRecorder, except in this case, we're essentially measuring the whole area of the window, which is defined using various parameters. And essentially the proportion of black to white pixels produces the surface intensity value, or this new parameter which we're calling surface intensity. And here we are working with very high resolution images. The resolution in this case is on the order of 75,000 dpi, so more than an order of magnitude greater than what we have from the scanner-based systems. We can look at an example of what the surface intensity data look like compared to blue intensity. So here we have an example of Picea abies from Slovakia with a replication of 14 series, and this is basically what the blue intensity Lakewood maximum blue intensity values look like. Here is the delta blue intensity version of that, so corrected for discoloration using Earlywood blue intensity values. And when we look at the surface intensity version of this, what we can see is very similar mean levels to maximum blue intensity, with the difference that there's considerably more variance in the data set and in this time series. And particularly what's notable is that in negative extreme years, or years with very pronounced negative extremes, the surface intensity actually has considerably lower values in those years. So hopefully this is a good sign that actually we're capturing, doing a better job of capturing these negative extremes. Looking at the inter-series correlation and express population signal statistics, we see that with the R-bar, even with a relatively low replication of about 6 series, the maximum blue intensity hovers around 0.2 to 0.3 R-bar, and this is equivalent to considerably lower than this commonly used threshold of EPS 0.85, which we commonly use. And so basically looking at the delta blue intensity version of that, it's very similar, just a little bit weaker in the more recent period here, likely as a result of adding in a bit more noise through the process of the statistical calculation of the delta blue parameter, but essentially the same. And if we look at the surface intensity, the R bar is considerably stronger, so around 0.6 for the most part, with some weaker periods, and this is equivalent to an EPS of above 0.85 for most of this time period. So that's quite encouraging because it suggests that we have a stronger signal with essentially when using the same number of series, and this is a situation where with blue intensity we would actually need many more samples in order to achieve a robust chronology. With surface intensity, this is much easier to achieve, and fewer series are required. So if we look at another example and another data set, this time in this case it's Pinus sylvestris from Finland, and a data set that Jesper has worked with quite extensively. Here we see the optimal seasonal temperature for density and blue intensity and so on. And we can have a look at the blue intensity chronology constructed or developed from a relatively large number of series, more than 80 series in this case. So we see variable periods with greater and reduced agreement, and at the same time we can also look at the inter-series correlation, the 31-year running correlation between the blue intensity chronology and the temperature data set, and so we can kind of see how that fluctuates over time. And if we look at surface intensity chronology based on only 12 series, we can visually see just how well that fits. In this case, clearly there's a bit of an improvement in terms of the fit compared to blue intensity. And also looking at the running correlations, we can see that actually throughout the whole period, surface intensity surpasses the results that we see with blue intensity. And looking at the correlations, blue intensity correlates at about 0.6, where surface intensity, the correlation in this case is 0.71 almost, so a considerable difference. And this is really an extensively evaluated data set with essentially a range of different parameters from blue intensity and density and anatomical parameters generated from the same samples, or the same trees at least. And so we can see this big spread of the sort of lower resolution samples, or lower resolution data sets, which correlate in the region of 0.55 to 0.62 or 3, with lower resolution anatomical data sets performing a bit better. And then with the higher resolution data sets, we see maximum liquid density a bit better still, and the best performing are the high resolution anatomical data sets. So with surface intensity, what we actually see is the response and correlation somewhere on the level of the X-ray density measurements, which is quite nice and quite encouraging, I would say. So another example here with a different region, Pinus sembra from Ukraine, and here we have a chronology composed of 10 series, but in this case actually what we're looking at is the alignment of the series and building of the chronology in relation to the Hartwood-Sapwood boundary. So what we have here is the sort of darker inner portion of the sample and the lighter outer part. And so when we average these together, we see that there's this very pronounced dip and a step
change in terms of the values in the maximum late-wood blue intensity value data set. Looking at if we have a look at the early-wood blue intensity, the values sort of show a corresponding increase when we compare the hardwood and sapwood parts of the sample. And just in this case, the values are positive rather than negative. This is just related to the inversion of the late-wood blue intensity values. And when we look at delta blue intensity, which is intended to actually correct for this color-related bias, we see that this actually performs quite well with values before and after more or less along the same level, a little bit higher in the sapwood part. And now looking at the surface intensity without any sort of statistical corrections or adjustments, we see that the mean values that we see in the period before this step change that we see in the late-wood blue intensity values, those same the spread of the data essentially stays quite close to that mean level and does not really, we definitely do not see any pronounced departure in this case. So again, I would say this is quite encouraging, and it makes sense because essentially we've been able to eliminate any color related issues just by eliminating color altogether. So with blue intensity and QRecorder, we essentially measure blue intensity using this window-based system and defining a bunch of parameters in order to characterize a certain part of the ring. And this works very well, but when it comes to surface intensity, the program is not really designed to represent this parameter very well from the binary image of black and white pixels. So we have to think very carefully about defining the parameters, or how we use the different parameters to produce a surface intensity value. For example, we might try to have a fixed width or size, the sort of the radial width of the windows that we are using, in order to try to capture the area, in this case, which has the highest density, sort of towards the outer part of the ring. So that could be fixed, or it could be proportional to the radial, the width or the radial size of the ring. For example, we could look at 20% of the ring, or 10% to try to really get as best or as accurate a representation of the part of the ring with the highest density. And if we look at the inner series correlation of some of these different parameterizations of the program, what we see with the fixed pixel width or width of the window in terms of number of pixels, the common signal inner series correlation is not too bad, but it can actually be improved in this case by using a wider window. And actually, if we look at the percentage size of the windows, then 30% performs even better. 20% is better still. 20%, and the inner series correlation then starts to decrease. The common signal weakens as we get to 15%, 10%, and 5% with a dramatic drop. This essentially indicates that as we get to these really narrow windows, we start to see a greater influence of noise, which is a big issue, because essentially right now we are not able to accurately capture the highest the points with the highest density accurately without also including a lot of noise. So this is something that potentially could be improved in the future. So I showed this before, basically the performance of surface intensity data in relation to other parameters generated from the same samples. So that looks quite good already. But actually, when we look at how we currently measure surface intensity using QRecorder, or I guess any other program that's currently available, one of the issues that we have is that with sort of the box and the window sort of area that we're using to actually capture this parameter, the issue is that we're not really following the boundary of the ring very well in some cases, which means that rather than just having a very nice well-defined signal of the densest part of the ring in terms of the Latewood surface intensity value, what we're actually getting is potentially in some cases a bit of a dilution of that signal and introduction of noise, for example, by including the early wood, some of the early wood of the next ring. And so this is a bit of an issue currently, which hopefully will be resolved with new measurement software options in the future. But essentially right now we're not utilizing the full potential of this parameter. But even so, you know, we can see that actually this is performing already quite well. But in theory, if we could actually fully utilize and maximize the full potential that this parameter has, there is actually no reason why we shouldn't be able to achieve the same sort of performance as high-resolution anatomical data sets. So this was a bit of an introduction to the surface intensity parameter, which is essentially a new high-resolution training parameter based on binary images. And just some of the advantages that we talked about or covered is the high resolution of the images, which is quite important and useful. We can essentially eliminate color biases by taking color out of the equation altogether. And of course, this potentially affects blue intensity data sets in a range of different settings, so that's quite important, I would say. Surface intensity has a stronger common signal compared to blue intensity, and that can be very useful, particularly in situations where the number of samples is quite limited, particularly back in time within a paleoclimatic setting, for example. The surface intensity data sets also have a very strong climate signal. I guess in most situations this should be better than blue intensity, but potentially it could be as good as quantitative wood anatomical data sets under optimal conditions, I would say, or when we can measure this parameter in the best possible way. It should also offer us the option to better represent climatic extremes, particularly negative extremes, and perhaps even offer a unbiased version of surface, sort of the density of the early wood, or the surface intensity version of that, which cannot really be achieved with early wood blue intensity, which cannot be corrected for color-related issues in the same way that late wood blue intensity can. So as part of ongoing, or if we look at some ongoing work, there are some questions about whether or not we could potentially speed up some of these processes, reduce the data that are the size of the data sets that are generated, maybe even lower some of the costs, even though it's not a very costly parameter to generate compared to some other, density, X-ray density, or even the anatomical data sets. We can start to look at other species and environments, including hardwoods and maybe even tropical environments. And of course, with the high resolution, we can start to look at intra-annual information as well, which is quite interesting, and potentially even start to measure quantitative wood anatomical parameters from surface image based, from surface images converted to a binary format. So SQWA that's something that we could call it potentially.
So thank you for listening. I hope you found the talk interesting. Feel free to contact me if you have any questions, and I hope you'll enjoy the rest of the workshop.